This is section 4.2, part C. In the last of the operations on rational expressions, we're going to be dealing with what we call complex fractions. A complex fraction is a fraction in which either the numerator, the denominator, or maybe both, contains another fraction, and we then call it a complex fraction. The first type that I want to talk about are fractions where the numerator and the denominator consist of just one single term. We're going to treat these as division problems, and so there's not going to be any real difference between these and stuff that you already know. Here's what I mean. If I've got my complex fraction with one fraction on the top and another fraction on the bottom, this main big fraction bar can just be treated as a division sign. And we know how to divide fractions. We just take the reciprocal and multiply. So I'm going to start here by rewriting the top fraction and then say let's change to multiply by the reciprocal of the bottom fraction. So just think of it as another way to write division. Of course, this doesn't get us out of the whole process of having to factor a whole bunch, right? So we still have to do that. So let me see here. I'm going to try and do some of my factoring off to the side. With the x cubed plus 27, I see that as a sum of cubes. And my sum of cubes formula is a plus b times a squared minus ab plus b squared. In this case, our a is just x, and it looks like the b would have to be 3. So a plus b, I'm going to put this right on the top of the fraction. A plus b is x plus 3. A squared would be x squared minus ab would be 3x plus b squared, which is 9. All right, the denominator is a trinomial, but not an a equal 1. So it's also going to take a little bit of extra work. Looking for a sum of negative 11 and a product of 10. Definitely negative 1, negative 10 is the only way to do that. So I'm going to split up that middle term as a negative 1x minus 10x. And then I still have the plus 5. Factoring that by grouping, I can take out an x, which gives me 2x minus 1. Minus sign between the groups, and I'll also take out a 5, which makes that 2x minus 1 as well. 2x minus 1 is the common binomial. And when I factor that out, I'm left with x minus 5. So that's my denominator. All right, second fraction, I think the factoring is a little easier, thank goodness, because I'm out of scrap room. All right, we can factor an x out on top. That gives us 2x minus 1. And the bottom is a trinomial, but it's an a equals 1. So I know it starts with x times x, which is a big advantage. I'm then just looking for a sum of 9 and a product of 18. So 3 and 6. Phew, that's a lot of factoring. All right, let's see what we've got. X plus 3 divided by x plus 3, that's positive 1. And 2x minus 1 divided by 2x minus 1 is also positive 1. I think that's everything. So on the top, multiplier is just 1 here. I still have this x squared minus 3x plus 9. And in the denominator, x minus 5 times x plus 3. All right, let's try a couple more like that, just special cases that actually come up quite a lot when you start looking at higher level math, and sometimes they're not difficult, but unless you remember exactly how to handle them, they can be easy to get stumped by. So looking at number 2, our numerator is a fraction, but our denominator is not. In order to treat this as a division problem, you're going to want to start by thinking of that denominator as x squared over 1. Now when I think of this as the division of two fractions, I can go back to that idea that we multiply by the reciprocal. So I have my numerator, the top fraction, multiplied by the reciprocal of the denominator, which would be 1 over x squared. I really like this problem because there's no factoring that can be done. Saves us some time. In fact, the only thing I really see here is we could say x divided by x squared. When we subtract the exponents, remember that's an x to the first. That would leave us x to the first in the denominator. So 4 times 1 is 4. And on the bottom I've got a factor of x times that x minus 5, which I will leave in factored form again. Number 3 is a very similar problem. The difference here, of course, is that the numerator this time doesn't look like a fraction. It's just 4x. And that's being divided by the fraction x minus 5 over x squared. I'm going to do the same thing as before. Even though that doesn't look like a fraction, I can treat it as a fraction. So I'm going to think of that as being a 4x over 1. Then I'll multiply by the reciprocal, which is x squared over x minus 5. Once again, kind of a nice one, nothing to factor here. And as a matter of fact, I don't even think there's anything that I can divide out. Remember, this is not multiplication here, it's subtraction, so I can't try to divide those x's. I think all I can do is multiply. 4x times x squared would be 4x cubed, and the bottom 1 times x minus 5 is still x minus 5. So, a lot of complex fractions really just boil down to a fancy way to write a division problem. And if you recognize them that way, you can use the techniques we already know to do the problem. There is a second type of complex fraction. In these problems, you'll notice that in the numerator, denominator, or both, there's more than one term. Here there's 3 terms. Here there are 2 terms. In that case, I cannot simply multiply by the reciprocal because I can't take the reciprocal of 2 terms at the same time. Instead, there are a couple of options. One option is to simply do the adding and subtracting on the top, do the adding and subtracting on the bottom, and then you'll have something that you can treat like the problems on the previous page. That is perfectly fine, and if you'd like to do them that way, I would encourage you to go ahead and do so. I would like to show you another option, which I think is a little bit shorter. In a case like this, what I like to do is look at all 5 of these small fractions and say, what's the LCD of all 5 of them? Well, that x cubed, the highest power of x, is the LCD for all of them. So what I'm going to do is I'm going to multiply by a form of 1. Specifically, I'm going to multiply by the LCD x cubed over itself. Some people find it easier to think of this as x cubed over 1 and x cubed over 1, and if that's true for you, by all means, feel free to do that. Because the next stage is going to be to distribute the x cubed all the way through the numerator, and then also all the way through the denominator. When I do that, I'm going to write this out this time, but as you get good at this, you may find that this next step is something you can do mentally. Multiplying the first fractions would give me 4x cubed over x minus 8x cubed over x squared plus 3x cubed over x cubed. On the bottom, first fraction becomes 2x cubed over x minus 3x cubed over x squared. Each of these small individual fractions should now simplify to a non-fractional term. Here we would have 4x squared minus 8x to the first. Notice I'm just subtracting exponents. Here the x cubed over x cubed is just 1, so all I'm going to end up with is a plus 3. On the bottom I would have 2x squared minus 3x to the first. All right, I think we're done. I probably should double check, but I don't think this factors. A sum of -8 and a product of 12, I don't believe is doable. So I think we're good to go. All right, let's try that same idea on number 2. I see two small fractions within the larger fraction. So the LCD here would be x plus 1 times x minus 1. Again, I'm going to multiply the entire big fraction here by that LCD. X plus 1, x minus 1, x plus 1, x minus 1. Always multiplying by the same thing, top and bottom. It's just a form of 1. If you liked having that little over 1 here and here, go right ahead. And then I have to distribute that to the top and also to the bottom. All right. So the first fraction, on top I'll have 3, x plus 1, x minus 1. And on the bottom, x plus 1 times 1 is just x plus 1. Plus, this 2 is just going to end up having to be multiplied by x plus 1, x minus 1. And the division by 1 there doesn't change anything, so I'm not even going to write it. On the bottom, same idea here. This 4 has to be multiplied by the whole x plus 1, x minus 1. 1 on the bottom doesn't change anything, so I won't write it. Minus, here I'll have 5 times x plus 1, x minus 1 on the top. And then x minus 1 times 1 is x minus 1 on the bottom. I can divide out those x plus 1s, that's just 1. Distributing the 3 makes that 3x minus 3. Plus, I'm going to keep the 2 out here for now. And if I multiply those together, that's x squared. The minus x and the plus x will add up to 0. And I'll just get a minus 1. Same idea on the bottom. I'm going to keep the 4 out here for now. And there's that x plus 1 times x minus 1. Or x squared minus 1 again. Minus, and here x minus 1 divided by x minus 1 is 1. Get rid of those. Distributing the negative 5 makes that a negative 5x and a negative 5. Be careful with that minus sign. All right, we're almost there. On the top, if I distribute the 2, Makes that 2x squared minus 2. And same idea, I'll distribute the 4 on the bottom. And let's see here, combining some like terms. On the top I've got 2x squared plus 3x, and that'll make that a minus 5. And on the bottom we've got 4x squared minus 5x, and combining those will make that a minus 8. Oh, whoops. How did I manage to miscopy that? That was 5x minus 5, wasn't it? So that should actually be a 9 there. You can double check on that, but although I think they do factor, I don't believe this reduces, so I'm just going to leave it in that form. Leave it to you to double check the factoring and make sure on that one if you want to do so. All right, that brings us to the end of 4.2.